So the previous equation, this, the previous function, this, can be written like this using pi matrix, big pi matrix, and y vector. Consists of all pi x1 through pi xn and y1 through yn. Okay, and this equation is actually equal to pi x transpose big pi matrix times pi matrix transpose pi matrix plus lambda I. So here the identity matrix is the dimension of pi, but here this identity matrix is n by n, dimension of y. Inverse y. And this matrix is the kernel matrix, consists of kernel of xi and xj. And this value is kernel vector between xi and x. Okay. So from the kernel function, you can define the prediction function, this fx. Okay. So you don't need to compute the exact feature expansion pi xi, but you just need to find out the kernel function between any two input xi and xj, and between our training data point and new given input to predict output y. Okay, and why this and this is the same? So essentially, to understand this easily, you have to understand the singular value decomposition of pi matrix. So let's say pi matrix singular value decomposition is mu u sigma v transpose, and here the dimension of u is the dimension of the feature expansion times n, and this is the dimension of n by n. This is the dimension of n by n, and assuming the dimension of the pi, the new feature space is much bigger than the number of input data point n. Then what is this? This is u sigma square u transpose, and this is u sigma v transpose. So when you multiply this, what will happen is this part essentially becomes u sigma square plus lambda identity matrix n by n inverse times sigma v transpose. And you can change the location of this and this because both matrices are diagonal matrices. And from this, you can rewrite this one as this: u sigma square plus lambda identity n by n inverse v transpose. And since v transpose equal to v transpose v, this is equal to identity matrix, you can rewrite this u sigma v transpose v sigma square plus lambda identity matrix inverse v transpose, and this is original pi matrix, and this part is pi transpose pi plus lambda identity m by m matrix inverse matrix. Okay, good. So this is kernel Ricci regression because we introduced the Ricci cost function. And essentially this Ricci regression is almost the same with GP, Gaussian process. So Gaussian process is Bayesian approach. Basically here the Gaussian process assumes that f follows some predefined prior distribution, and the prior distribution usually just a zero mean and some identity covariance matrix. And here again the dimension of identity matrix is the same with the dimension of pi, so which is usually infinity. So what will happen if we f follow zero mean and identity covariance matrix? Basically the covariance between fxi and fx0, fxi and fxj. This is covariance matrix between the inner product between f pi xi and f pi xj, right? And how to compute the covariance matrix between two inner product? This is essentially expectation of pi xi transpose f transpose pi xj. So here this value and these values are constant, and only this part are random variables. So we take the expectation with respect to this randomness of f. And since the covariance matrix of f follow identity matrix, so this is equal to identity matrix. And so we have covariance matrix equal to inner product between pi xi transpose pi xi and pi xj. So the covariance between fxi and fxj is kernel value between xi and xj. Okay, so the Gaussian process concept is this: your f vector define your output function f, follow normal distribution 0 and identity covariance matrix, and here we use the kernel trick. So the function fx and xi and fxj is inner product between f pi xi and f pi xj. So when you compute the covariance between these two, we have this form and this kernel value. In the end, we have. Okay, this is the main idea behind the Gaussian process. And how to find f from this prior distribution? Same as before, we just learn some maximum likelihood method with this normal prior and try to optimize the and also assume that your real value fi is equal to fxi plus epsilon I, and epsilon I follows some normal distribution with mean 0 and sigma square. And using these two prior, we define likelihood value of your O P Y I for given xi, and then optimize your value f that maximize your log likelihood value. Then in the end, you have the same cost function like this, and you have almost the same solution with GP. So GP is another explanation of Ricci kernel method, and Ricci method is another explanation of Gaussian process. Okay, so Ricci kernel method, kernel Ricci regression, and Gaussian process, basically they are the same, but they explain equation in different concept. Anyway, Gaussian process is very useful. Still many people or many application, Gaussian process show very nice performance. So this is one very nice candidate when you want to learn something from your data. So I strongly recommend to use Gaussian process if you understand the uncertainty of your decision, because this is a very powerful Bayesian learning method. Okay, so this is very advanced topic and optional thing. But if you're really interested in machine learning, you have to understand this kernel trick and all related.